Okay, so we'll talk about radiography and fluoroscopy for the beginning. So we are on the first presentation. So generally, what is the RTG? RTG uses the X-rays. Yes, what are the X-rays? The X-rays are the part of the spectrum of the electromagnetic radiation, like light. So you can think about X-rays generally, so the rays, so the spectrum, so the electromagnetic radiation that gets through our organism during RTG, fluoroscopy and CT scan as some form of invisible light. Yes. So we have such type of light, such part of the spectrum of all of the electromagnetic radiation that is invisible and that is able to penetrate through the body tissues and see and show us what is inside. Yes, so let's get some picture. Yeah, oh, this is a good picture. So we let's look from the top. On the top you see those arrows. I cannot point this on the mobile. Just look and try to understand. So at the top you can see that we are producing some rays. Those arrows that are getting to the patient that is lying on the flat table are the rays. We are thinking about radiography and fluoroscopy, so we are thinking about X-rays. So one more time, X-rays is like this invisible light that can get through the person and show us what is inside. We'll get a bit more in details what exactly do I mean. So let's get here. Yes, so standard X-ray machine produces high energy photons. As you probably heard during your life, photons are the particles of light. Yes, of course the light has a dual nature. It can be thought also as a wave and also as a particle beam. It is quite complicated, but you do not need to know exactly about this. You just need to know that the X-rays is a bit like light. So, like light, it has photons. With high voltage electric current, this technical detail, not important for now. And we focus the beam towards the patient, yes, because we want this beam to get through the patient. Then pass through the patient to the film. They are absorbed by the patient tissues or they scatter, in which case will not provide diagnostic information. Let's get to the end and I will get one more time through it. As the X-ray reaches the cassette and interact with radiographic film, the energy is converted into visible light, which exposes the film and creates the familiar radiograph. In fluoroscopy, the film is replaced by an image intensifier, which allows a digital image to be seen on a television monitor in real time. Yes. So, okay. One more time, let's look at this. So you already know that we need to produce the beam of X-rays. This beam of X-rays is getting to the patient, through the patient, and on the cassette. Yes? So we have the radiography and fluoroscopy. It works nearly the same. The main difference between radiography and fluoroscopy is that the fluoroscopy is dynamic. So when we... Wait a moment. Oh, sorry. When we are shining this special light, those X-rays on the patient, and we are doing the X-rays, we are just would shine them on the patient for a very short time, and we'll see what is on the other side. Yes. So the cassette is just getting all of these rays that would get through the patient. And on the basis of what gets through, we'll get the information. So it is generally as you answered in your first question. So the main difference is that here we have a real-time images. So a time-based images. How we have the real-time images? It's generally like in the cinema. Yes, you probably heard in your life that we get in cinema we see the moving pictures. Yes, because we have a static picture that changes rapidly. So one more time, when we are looking at the video, any video, even this that you are looking now, it is a series of fast changing. Yes, so we get fast changing static images, and if it changes fast enough, it looks as if it would be moving. So when we get the radiography, the only thing that we do is we just take a series of the X-rays, and then we compose those series of the X-rays into the film that we can analyze. So you already see that we can get a little bit more information on the fluoroscopy. For example, if you want to know how the bowels are acting, yes, whether they are active or not active, whether the food bolus would get through or it stays in one place, yes, so whether the intestines are able to propel the food through itself, we need a dynamic information, yes, so we need to know at the beginning what happened and then how this food bolus propels, yes. So we can use fluoroscopy to this. Of course, we have other techniques also. Fluoroscopy now is relatively rarely used, but still it holds some role in, for example, in case of the intestines, yes, whether the intestines are able to act efficiently or not. Okay, so now exactly how we can see something on the film. This is quite important to understand the idea. Yes? Oh, I suppose this is a nice picture. So, when we shine the X-ray, yes, on the body, on anything, we'll see only those rays that would get through the patient, yes? Because, look one more time here. We are producing the X-rays on the top, and we are getting the film below the patient, yes? So we will see only those rays that gets through, yeah? So you can think about this a little bit as like shining the light through the piece of paper, yes? It would shine through those pieces of paper that are not dark, yes? When there would be a dark part of the paper, it would not shine through. You would see this shining through only of those parts that there are holes, for example, it would shine a lot of light through, or there are light colors or no color at all, it would also get through, but if it would be dark, it would not get through, yes? Here is similar. Now, maybe let's get back to this picture. Yeah. So we are measuring here how much of the rays gets through. So now you probably think on what it depends how much light gets through. Yes, it depends mainly on the density of the tissue. Yeah. So the more dense is the tissue, the less of the less of the rays would get through. Yeah. So less of the rays would get through, the less of them we would see in the end. So critical to think about this. So when we have something dense, it would stop it and you would not see anything, yes? If it would not be dense, it would not be stopped and we will see everything, generally speaking. Of course, there is a gradation. So some tissues, like bones are dense. So they will generally stop most of the X-rays, yes? And air air has very low density. So lungs, for example, would stop only very few X-rays. But the liver, for example, is between the bones and the lungs. So we have some gradation. On the basis of this gradation, we can see a lot of things inside the organism. Yes? So, I like this picture also. So, here you can see a radiographic demonstration of interfaces. What is the interface? The interface is very important definition in radiography. The interface is a border. It's not only in the radiography, it is in physics generally. So interface is a border between two bodies of different densities, in this case at least. So here we have a balloon with water and air. Yes. On the left, one more time. On the left, you can see a balloon that is filled with water in the vase with water. On the right, you have a balloon filled with air in the vase filled with water. Yes? And now, think for a moment why we cannot see on the X-ray, yes? On the left, generally, this left picture is X-ray. Why on the left, in this picture, we cannot see a balloon filled with water? Yes? Think for a moment. Okay, so I hope that you figured it out. Generally, in order to see something, we need to have an interface. Why? This is important, so try to concentrate. Maybe let's start from the beginning. As we already said a couple times, the only thing that we can see is there are the rays that gets through. Yes? So, if we are looking at some organ, maybe not. If we are looking at some organ and try to find something in this organ, we need to find something that is different. I know that for now it's not clear, but we'll get a couple of times through it. I suppose you will get it. So, one more time. Look at this balloon with air. Yes, this is this visible balloon generally. In this balloon with air, we have differences in densities. Yes, so when the X-rays gets through this balloon, they are not stopped. Yes, because this balloon is filled with air. But when the X-rays would get into the water, they would be partially stopped. Yes? So as you can see this darker spot at the beginning, this darker circle, we are still talking about this picture on the left, yes? The big picture on the left with two vases. So when you are looking at this black circle inside, this is black because more of the X-rays get through. Now one more important thing. Generally, for historical reasons, the darker something is, it means that there is more of the X-rays. Yes, the lighter it is, the less of the X-rays. From the historical perspective, it's not important to remember the history. Of course, I would just tell you because I suppose it makes it easier to remember it. Generally, historically, there was used salt of silver. So we get some film that was covered by the salts of silver, and those salts of silver, when they were introduced to X-rays, so when X-rays were shining on the salts of silver, those salts of silver would change chemically and would become black. Yes? So more of the X-rays, the blacker the picture. because it was like this 100 years ago. 100, not hundreds. Now, of course, everything is digital, but as radiologists get used to such pictures, they are still presented in that strange way a bit. So, one more time. Imagine, see that we have two mediums of different densities. In the center, we have air. On the borders, we have water. So when the X-rays get through, they get through easily through the air, and it's hard for them to get through the water. Yes. So we can see a difference. We can see the interface, because generally the only thing that you can see here is this border of the circle. Yes. So thanks to this, you can guess very precisely where the balloon filled with air is. Yes. So now let's get to the other example. The balloon filled with water. And as is obvious on the picture, we cannot see anything. Why? Because when the X-ray would get through any part of this body, it would have similar problem to get through. Yes? Because the balloon is filled with the water is around, so everything has generally similar density. And in case of the X-rays or CT scan, everything is about densities. So when the densities here are similar, we cannot see any difference. We'll see difference only when there is a marked difference in density. Yeah. Okay, I hope that you get it. If not, we'll get back to this idea a little bit more, and you can also, as always, post some questions on Facebook. So, or anywhere else that I will specify. Well, I suppose that this was pointed out. So, key points. The familiar radiograph is two-dimensional representation of three-dimensional structures of the patient body. So, obviously, we cannot represent everything because the X-rays are flat. Yes, the CT scans are 3D pictures. The X-rays and fluoroscopy also are only 2D. So the X-rays and fluoroscopy are only 2D pictures. So let's get back for a moment here. So when you are looking at this cassette at the bottom, so the cassette is this part that is collecting the X-rays and that is changing color, generally speaking, historically at least. When those X-rays are shining on it, it is flat. Yes. So obviously, what we will see is also a flat picture, the flat picture of the three-dimensional object, because we have a three dimensions. Yes, we can be fat or thin. We can have some tumor inside that can be top or down. But from the perspective here, whether anything is anteriorly, so at the near the surface of the skin, yes, near the umbilicus, for example, or deep in the abdomen, it would be the same, because we are looking top down. We only know whether it's on the left, on the right, superior or inferior, but we will not know whether it's anterior or posterior, or at least it would be hard to say. So we lose one dimension. Of course, we can also help us with this. So we lose this one dimension. Yes, we cannot say in this situation whether anything is anterior or posterior. Yes, we can say only superior, inferior, lateral, medial. Yes, like for example here. Yes, when you are looking at this balloon, you cannot say whether it's in closer to us or more distant to us in the vase. Yes, it would look exactly the same. If you would pop it up, you would see it. If you would pop it down, you would see it. Pop it to the left, yes, you will see it. To the right, you will see it. But if you would get it to yourself or more distant from yourself, it would look generally the same. Yes? So, think for a moment how we can alleviate this problem. How we can see something that is more to the anterior, more to the posterior. How we can recreate those lost information using normal RTG. Because historically speaking, the only imaging study many years ago, and still in some pure countries it holds true, is the RTG. And physicians and technicians needed to get the idea how to get this information, how to know whether something is anterior or posterior. Yes? So think for a moment. Okay, I hope that you got the idea. Generally, the easiest thing to do is to look from different perspectives. Oh, sorry. So you generally need to, for example, get the picture from the side. Yes, or oblique picture. Generally, get the picture from different perspective, from different sides. And if you would look from the side, you would know what is anterior and posterior, what is superior and inferior, what is top, what is down, what is to the anterior, what is to the posterior. But in this case, you will not know what is lateral or medial. But you will know what is lateral or medial on the normal pictures. Yes. I know that it may be a bit convoluted, but we'll get back to this also a bit later. So generally, if we want to see the dimension that is not seen on normal picture, we need to reorient the patient. Okay, so what is the computed tomography? Oh, this is a good picture. So computed tomography is a huge series of RTG. Yes, so we have, in order to get the CT scan of the body, we need to generate huge amounts of CT scans. Okay, so we generally need to get huge amount of X-rays in order to create one CT scan. Yes, so we get X-ray after X-ray after X-ray after X-ray. And what is important here? We are looking from different angles. So as I pointed out earlier, oh, maybe wait a moment, because this. Okay, so just to get it one more time, the idea what we can see on the X-ray. Yes, because this is important concept for whole of the radiology. So we have some sheet of paper. Yes, this sheet of paper can show us when some RTG would point out. Yes, so we would shine here, it would get dark here. Yes, if we would shine here, it would get dark here. Yes, so we are shining somewhere and this would get dark. Yes, the more of it would get, the darker it would become. Yeah, the less of it, if it would shine a bit, it would be less dark, so lighter. Yes, so the darker something is, the more it gets into. Yes, so now let's get from the side. You remember the picture of the patient. This is the patient, and these are those RTGs. Yes, but now we are looking from the side. Yes, so only this information that would get through, yes, like this, would be visible on this sheet of paper. Of course, this is the cassette. It's not sheet of paper. This is just the explanation. Okay. So now, what we can see on this patient? Let's change the perspective. Now we are looking at the patient from the top. Yes? Okay. Let's make it fat patient. So, for example, we have the abdomen. Yes? In case of the abdomen, when the light would get into it, most of it, of course not all, but big part of it would just shine through, because in the abdomen we do not have much bones. Yes, we have generally mostly organs, soft tissue, things like that, and it would get through. So now let's imagine that this is what is below. Yes, so here one more time we have somewhere here we have the abdomen. Yes, so we'll get it dark. Yes, when we are shining on the legs, generally some of it would be absorbed by the bones, so it would not get through, but everything around the bones would get. So we will not see the bones, we will see everything around. Yes? What would happen on the chest? On the chest, as I told, we have lungs. In case of the lungs, nearly everything would get through. Nearly everything would get through. But we'd also have ribs and heart. So through the ribs, between ribs, it would shine through, but the ribs would stop most of RTG. And we have the skull. Yes, the skull is generally big bone. So nearly nothing would get through. Only would see everything that is around, but the skull would not be visible. Yes? So it would be light. This is important. Yes, so we'll only see this what gets through. So now, also try to think about this. When we are shining on this abdomen, we'll count how much of it would be stopped by whole of the abdomen. Yes? So now let's look for a moment at the body from the side. Yes, let's make this abdomen. And this is face. So when we are shining the X-rays down, it's like that. And we only would count how many of them would be stopped. So if let's imagine that we are looking for a tumor. Yes, if the tumor would be here, or if the tumor would be here, this would look exactly the same, because imagine the tumor. Let's now concentrate about this. The tumor is here, so we are shining the light, and it stopped. It would not get. So we would not get any information here, yes? It would generally look like a blank spot, like a hole. So it would be light. So now let's get concentrating on this point, yes? This is the same. It would get through and, stop. So it would not get through, yes? And we will have a hole here. One more time, the hole is light. When an X-ray gets through, it's dark. So here it tries to get through, but it can't because there is a tumor. Yeah. Of course, just to be precise, not all of the tumors would stop the X-rays. You have different types of the tumors. Some are radiologically dense, some are not. Some would not be visible at all on the normal X-ray. Okay. Sorry, and one more thing. So, also, why I am showing this to you? I'm showing this to you that on normal X-ray that you are looking from the anterior to posterior, posterior to anterior, never mind, we cannot say whether anything is to the anterior, so here, or to the posterior. We are losing one dimension. Yes? So we cannot say anything about this. We can say, for example, yes, this is top, this is left, this is right, this is bottom. True. But how deep it is, yes? Show me, look at this picture, yes? I know that I'm not artist, far from it. but you are not able at all, even if it would be the real RTG, to say whether anything is anterior or posterior. It's just impossible. At least very hard. But if you would get different picture, yes, like this, from the side, now the situation is different. You can say what is anterior and what is posterior. Yes, what you can say what is superior, what is inferior. But you cannot say what is lateral and what is medial. Because if you shine the ray through this, you'll just know the location. Anterior, posterior, superior, inferior, but not medial lateral. So when we combine different pictures, we can combine them into the 3D image, generally speaking. Of course, in case of the classical RTG, it's a bit hard to organize efficiently. However, in case of the computer tomography, it's highly efficient. Generally, it's quite complex computationally. Yes, you need a lot of the brain, or better, a lot of powerful computers that would process the image to get from a huge amounts of simple X-rays one 3D scan. Yes, so we'll change the multiple X-rays into the information about the 3D orientation of the organs. So now we know what is anterior, superior, lateral, medial, posterior, everything. And we also get far better resolution. So we'll see a lot of pictures of RTG and CT scans, and you will see that on RTG it is hard to discern anything. On CT scans you can see really well a lot of details of our organs. Yes, so this is very important difference. We get on RTG only the basic things, generally the big things. On CT scan we see far more. Okay, and what is the Hansfield scale, the HU scale? Okay, so as you said, the Hansfield scale is the value that is used in the CT scan that tells us about the physical density of tissue proportional to the absorption or attenuation. What does absorption and attenuation means? Because you use this in your answers. This generally tells us how much of the X-rays were stopped. As we previously shown, yes, what is critical is how many of these X-rays would get through. Yes, if it would get stopped, or it would get through from the top to the bottom. Yes, so in the X-rays we are just looking and telling. Yes, generally if there is a lung, so a lot of get through. Here in abdomen, there is higher density, so we get the idea that less get through. There is a bone, so only a little get through. But in case of the CT scan, we can measure exactly how much get through, and we can show this on the graph. And this is critical difference also. So we are very precise in case of the CT scan. So this is critical point. We can measure exactly how much of the CT scan gets through, and what is the orientation of each organ in the body. And on the basis of it, we can diagnose what is happening. Yes. So the Hansfield scale is generally, as you said, says us about attenuation. So attenuation is generally how much of the X-ray is stopped, how much of this beam of photons is stopped. Good. So CT is computer tomography. Is a method of using X-rays to produce axial images of the body. These images are viewed as if looking from the feet up towards the head. CT is more sensitive than conventional plain film in distinguishing differences of tissue density. So we already talked about these interfaces with the example of the balloon. When we have the interface between the air and the water. So when we have this small difference in density, for example, kidneys have similar density to the liver. It's hard to discern on normal X-ray kidneys from the liver. It's possible, but it's not easy because their density is similar. On the CT scan, it's very easy because CT scan is far better in discerning small differences in densities. You will see this on the picture also. Common uses of CT include examining any part of the body where the fine anatomic detail of subtle distinction between tissue types is necessary for diagnosis. So generally, CT scan, when you perform the CT scan on the patient, you would see more. It's true, not. It's from the amount of information that you can get through the CT scan, it's always better than the RTG. So, why to use RTG at all? There are two main answers for this. First of all, obviously, RTG is far cheaper and faster. And it's important. So, we can perform a lot of RTGs, and to be honest, for example, to simple fracture, RTG is enough. We do not need CT scan for simple fracture of the middle part of the bone, for example. For some fractures, yes, we need it. But for some fractures, we do not. The other thing is the radiation dosage. We'll also talk about this a bit more. But generally, these X-rays, this radiation has high energy. And it can be potentially harmful. So we generally do not want to expose a patient to the X-rays if it's not necessary. And in normal classical X-rays, for example chest X-ray, the amount of radiation that gets to the patient is hundreds or thousands times less than in computer tomography. Because, as we already talked about, the computer tomography is generally hundreds of the X-rays combined. And we cannot get around it. So we trade the better resolution for higher dosage of radiation. Yep. Okay. So now, in the next video we'll tell a couple words on nuclear medicine also.